What if machines could learn? Not by being told every rule, but by discovering them on their own. Behind every smart assistant, every self-driving car, and every chatbot lies a hidden process, a silent education happening inside silicon minds. Today, we step inside that process to uncover how machines actually learn. For most of computing history, humans had to program every instruction. If A equals B, then do C. That's traditional code, but learning changed everything. Instead of hard coding logic, we now teach algorithms using data. We don't tell them what a cat looks like, we show them 10 million cats. Through repetition, error, and correction, the machine forms its own internal rules. This is machine learning, and it's the beating heart of modern AI. At its core, every learning system is an equation trying to minimize error. Imagine a line drawn through a scatter plot. That's a model. Each time the line misses a data point, it adjusts. That adjustment is called optimization. In practice, AIs use a method called gradient descent, the mathematical art of improvement. Picture a mountain range of errors. Gradient descent finds the path down to the lowest valley, the point where the model is most accurate. Every step it takes downhill makes the machine smarter. It's not conscious effort, it's math seeking balance. The idea came from biology. Our brains contain about 86 billion neurons, each firing tiny electrical signals. Artificial neural networks mimic this pattern with digital neurons. Each neuron receives numbers, multiplies them by weights, adds a bias, applies an activation function, and passes the result forward. Millions of these neurons form layers, input, hidden, output, and together they learn to recognize patterns. In the 1980s, this seemed impossible to scale, but in 2012, GPUs changed everything. Suddenly, computers could train networks with millions of parameters in hours instead of years. That breakthrough, deep learning, is the reason AI exploded. Not all learning is the same. AI learns through 3 core methods, each inspired by human education. Supervised learning, like a student with a teacher, the model sees labeled examples. This is spam, this is not. Over time, it memorizes patterns that link input to output. Unsupervised learning, like exploring without labels. The AI organizes data into clusters, discovering hidden structures, the natural groupings of language, images, or behavior. Reinforcement learning, the art of trial and error. Like a child playing a game, the AI tries actions, receives rewards or punishments, and improves its strategy. This is how AlphaGo defeated the world champion in Go. Each method adds a different layer of intelligence. Together they form the learning trinity. If algorithms are the brain, data is the food. The quality of AI depends entirely on the data it feeds on. Early AI researchers spent years crafting features, hand-designed clues like edge detectors for vision or keywords for language. Then came representation learning, the ability for machines to find features themselves. Deep neural networks automatically extract hierarchies of features, from pixels to patterns to concepts. This shift turned AI from a handcrafted tool into a self-discovering system. How does a network actually learn? Through a loop called backpropagation, the engine of modern AI. Here's how it works. The network makes a prediction. It compares the output to the correct answer. It calculates the error. It propagates that error backward through the layers, adjusting weights to reduce future mistakes. This cycle repeats millions of times until the model's predictions match reality within a tiny margin. That's why training requires huge computational power. Massive GPU clusters run for weeks, tuning billions of connections. When the training ends, what remains is a map of relationships. A mathematical model that has learned from experience. For decades, neural networks used simple feed-forward structures. Then came a series of architectural revolutions that redefined how machines learn. Convolutional neural networks for vision. They slide filters across images to detect patterns like eyes or edges. Recurrent neural networks for sequences. They remember context across time. Transformers, introduced in 2017, changed everything. They don't learn sequentially. They learn relationships between every word at once using attention. That attention mechanism, literally called self-attention, is the core of ChatGPT, Gemini, Claude, and almost every modern AI. Transformers allowed machines to understand context, reason, and generate coherent thought-like responses. They gave language models a form of memory and creativity previously unimaginable. Learning is powerful, but dangerous. A model can memorize training data too well, failing to generalize to new situations. This is called overfitting. To prevent it, researchers use techniques like dropout, data augmentation, and cross-validation. The goal is balance. Learn from the past without being trapped by it. Then there's bias, when the data reflects human prejudice. AI doesn't invent bias, it amplifies it. If historical data is unequal, predictions will be too. True intelligence requires fair data, ethical design, and constant human oversight. The 21st century brought a new paradigm: scale. Large language models like GPT are trained on trillions of words. Instead of hand labeling everything, they learn from self-supervision, predicting missing pieces in data. It's like teaching a child to finish sentences. Over billions of examples, the model internalizes grammar, facts, and logic, not because it's told, but because it observes. That's why modern AI feels intuitive. It doesn't just see patterns, it anticipates them. This massive scale is what powers the next generation of intelligence, machines that learn from the entire internet. What's next? Three directions define the future of machine learning: few-shot and zero-shot learning. Models that can learn new tasks from a handful of examples, like humans do. Continual learning, systems that update knowledge without forgetting the old. Causal and reasoning-based, AI, understanding why things happen, not just what comes next. We're teaching machines to understand cause, effect, and context, the foundations of true reasoning. Combine that with quantum computing, and learning could accelerate beyond our comprehension. When a neural network learns, it builds an inner representation of the world. It doesn't store images or words, it stores relationships, mathematical connections between concepts. To the machine, cat, dog, and lion exist as vectors in a multi-dimensional space. The distance between those points defines meaning. That's how AI can compose music, translate languages, and even invent new ideas. Inside the mind of AI isn't a soul, it's a geometry of thought. Every time a machine learns from us, it reflects us back. Our data teaches it our logic, our creativity, and our flaws. In a way, machine learning is a mirror for human learning, a digital extension of our own intelligence. As machines get better at learning, we're forced to ask, what does it mean to know something? To understand? To be aware? The answers may not lie in the machine, but in ourselves. We've traveled through the neural landscapes of machine intelligence, from math and data to networks and reasoning. We've seen that machines don't think like us, but their learning reveals what thinking really is. The mind of AI is a map of human curiosity, encoded in code, built on billions of examples, and still learning. If you want to keep exploring the frontiers of intelligence, subscribe to FutureGen Learning, where we decode how machines learn, think, and create the future.